What's up? I'm Vin, and today I want to go through an AP Calculus AB/BC Unit 7 practice test. I'll leave a link to a copy of this test in the description below, so let's get started. So question 1, we have a slope field and we want to match it to a differential equation. And for these, I like to think of slope guy. So here's slope guy over here, and the way slope guy works is that anytime you have a positive slope, your line or your curve is increasing. Negative slope, your line is decreasing. If you have an undefined slope, your line is going to be vertical here. And if you have a zero slope, your line is horizontal. So when I look at these slope fields, I always look for something like a zero slope or a vertical slope. And I notice over here that when y is equal to 2, so think about this, when y is equal to 2, the slope, but in calculus we call the slope dy dx, is equal to 0. And then the next location here, if we look over here along this vertical section, that along the line x equals negative 1, we're to the left of the y-axis here. Along x equals negative 1, we also have a 0 slope. So now what I look for in the answer key is a situation where we have a differential equation where the factors give us these two roots. So right away, just looking at this, I'm seeing choice A is going to be our answer. Because if we set this equal to 0, this is going to be true when we have y minus 2 equal to 0, or we could have x plus 1 equal to 0. And notice this gives us the solutions y equals 2, and we have x equals negative 1. So choice A is looking good. So question 2, we have a differential equation. We have a point that's on the solution curve, and we want to solve for the function f of x. Now, just so that the notation matches up with the question, I'm going to pretend for a moment that all of these are the correct answer, but they're obviously not all correct here. So what I look for first when I'm trying to do this without separation of variables is I try to plug this point into the answer choices and see if it actually does check out. So right away, just looking at this, I could see that choice D is no good and choice A is no good. And the reason I could just do that so quickly is, let's say choice A, if I have y equals e to the negative x, in this case we have x is equal to negative 1, y equals negative 2. And if I plug that in, I'm going to have negative 1 is 1, minus 1 is 0, and then plus 3. And this would actually give us 1 plus 3, which is 4, not negative 2. So that's why this one's out. And then a similar argument here will tell us that choice D, that would give us e to the negative 1 plus 1. We have the same situation here, that the y value is not matching up. So that's why those two are out. But now let's say we explored choice B and choice C. Well, if y is equal to, we have e to the negative x minus 1 and then minus 3 like this. Let's see what happens here with this answer. If we plug in negative 1, we are going to get y equals negative 2. But the next step then to verifying if our equation is a solution is we have to take the derivative. So this is going to be e to the minus x minus 1 times the derivative of negative x minus 1 is minus 1. And then the derivative of minus 3 at the end is just 0. So now if we try to plug this into the differential equation over here, that would tell us we would have negative e to the minus x minus 1 equals y plus 3. But the problem with this is that when we plug this in, so we have y, that's this piece here, plus 3, is that the exponent terms here are off by a negative. So just by process of elimination, I know this is going to be choice C. But if I had to show that choice C is good, the initial condition does check out here when we have this equation here. If you plug in negative 1, you're going to get y equals negative 2. But when we take the derivative, this one is also going to check out. We're going to have just e to the x plus 1. Derivative of x plus 1 is 1, so chain rule is not super important here. And then from this step on, what we could do is plug into this differential equation the left side dy dx. We would have e to the x plus 1 equals, and we have y is e to the x plus 1 minus 3. And then we just tack on the plus 3. And notice here, this cancels out and we have a match. So choice C is definitely our answer. So question 3, we have a Roman numeral question, and we want to know which of these equations satisfies this differential equation. So for this one, I would just go brute force, finding the second derivative of all of these Roman numerals. So I have y prime is cosine, y double would be negative sine x. And notice if we do sine x plus the second derivative negative sine x, that is in fact going to give us 0. If we add the y double and the y term, this is going to equal 0. So Roman numeral 1 is good. Now, if we check this one, we would have y prime, and let's change colors here. So we have y prime equals the derivative of e to the minus x is e to the minus x times minus 1. But watch what happens when we take the second derivative here. This is going to switch back to positive e to the minus x, because when the negative 1 comes down again, it's going to make this minus a plus. So in this situation, we would have y double prime plus y is equal to, and that would give us e to the minus x plus y is originally e to the minus x. And notice here that this is not equal to 0. This would give us 2e to the negative x. So this one is out. And now if we look at the third answer choice here, we have y equals tangent x. And if we take the derivative, we're going to have secant squared x. If we take the second derivative here, we're going to have 2 times secant x, because we're using the chain rule here, so power rule on the outside. But then we have to take the derivative of secant, which is secant tangent. And just looking at this here, if we add tangent plus this is not going to be 0 for all x's. So that's how I know this one is also out. So choice A, 1 only. For question 4, we're going to assume y equals g of t is a solution to this differential equation here. And we have k is constant, and select values for g of t are given in this table above. Which of the following is an expression for g of t? So for this one, we want to know exponential models for differential equations. So anytime you have a derivative in this form, you could assume here that the solution is going to be in the form of y equals a constant times e to the kt like this. So you could do separation of variables and use these two initial conditions to get the value of c and k, or you could just know this concept once again, that this derivative will give you a solution in this form here. So then you just have to scan the answer choices, and you can see that choice D is the one that matches this form. The other two are obviously not it, A and B, but choice C, the problem with choice C is that the constant is being added instead of being multiplied in front. So that's how I know choice D is good. Now, once again, just knowing that basic idea gets you through this quickly, but if you did want to solve this by separation of variables, you would just have to plug in both initial conditions to solve for C and K, and you get the same result here, choice D. So question 5, we have a slope field, and we want to find a potential solution curve to the slope field. So let's say we pick out a point over here. The way slope fields work is that you want to draw your curve in the direction that the little lines are pointing. So obviously, don't draw something crazy like this that's really just going against the direction of these little slopes. You want to follow this path here like this. Notice the y-axis, we have a vertical asymptote, so that's why I'm going this way, and then I'm going to go this way for the rest of it. And then if I were to go over here, let's say in this quadrant, notice that we would have something looking like this. So we have to show up to the AP test knowing some of the basic curves here. So right away I could see that this is matching 1 over x. Now the reason why I know it's not this one is that 1 over x squared, what that does is it takes the part of the curve here in quadrant 3, and in a sense it flips it up to quadrant 2, and it also makes it go to the x and y axis at a faster rate. So that's how I know choice B is out, because this one is not going up like this. We would be going against the slope field. And now I know this isn't sine x because sine x is a waving function like this. And if we look at this graph here from -5 to 5, this is clearly not making a sine curve. And then tangent inverse x here has 2 horizontal asymptotes, one at pi over 2 up top, and it has another horizontal asymptote down here at -pi over 2. And this curve looks like this. So that is clearly not what we're looking at in this picture. Choice A is our best option. So question 6, we have another slope field, and here is the differential equation for the slope field. And what we're told is that y equals f of x is the solution with f of 2 equal to 1. So I'm going to go over here to the point 2, 1 and just plot this point. And now what we want to find is what is the limit as x approaches infinity of f of x. So following this slope field like this, we're going to be going in this direction, but notice at y equals 3, we have a horizontal asymptote like this. Okay, so here's our horizontal asymptote. If we were to go the other way, so let's say we're going this way like this. This is just a rough sketch, but we have a horizontal asymptote going in the other direction towards negative infinity as well. And the way I know that these are definitely our asymptotes at 3 and at -1 is based on the differential equation. If we look at when is the differential equation dy dx equal to 0, this is true when each of those factors, when y plus 1 equals 0 and when y minus 3 is equal to 0. And this would give us solutions y equals -1 and y equals +3. So just looking at this here, if we want to find what is the limit as x approaches positive infinity, notice that we're going to get cut off here by this horizontal asymptote at y equals 3. So that is our limit. Choice C is our answer. So question 7 is a lot like question 6, except now we don't have a slope field. So we just have to use the differential equation. We have y equals f of x is a solution to this differential equation here, and this is the initial condition. we want to find the limit as x approaches infinity of f of x. So for this one, the first thing I would find is when is dy dx equal to 0? And this is going to be true when 3y is equal to 0 and also when 5 minus y equals 0. And this gives us two equations for our horizontal asymptotes at y equals 0 and y equals 5. So I'm just going to do a little sketch over here. So at y equals 0, that's the x-axis. We have a horizontal asymptote. And then also at 5. So this is just getting a sketch going here like this. And once again, we know this to be true because when your derivative is equal to 0, constantly across the board for all of these y values, that in a sense is making your horizontal asymptote where the slope starts to head towards 0. So now we're going to use this initial condition, f of 0 is equal to 2. And what I would verify here is to make sure that this curve, our solution curve, is either increasing between 0 and 5 or it's decreasing between 0 and 5. So we need to investigate what is going on when we have a y value between 0 and 5, because notice the derivative is all in terms of y. So let's say you pick out something random like y equals 2. If you were to plug in y equals 2 to the derivative, then what you'd have here is you'd have 3 times 2 times 5 minus 2. And the first thing that jumps out at me is that this is positive. This is 6 times 3, which is 18. So this is like pretty steeply increasing. But then all the slopes here in this space are positive. As we get closer to 5, the slope is heading towards 0. So if I start to sketch this solution curve, it's increasing pretty steeply here. But then very, very quickly, it starts to taper off. So let's just draw that once more. So this is going up really fast, and then it starts to taper off like this. So if we think about this, what is the limit as x approaches positive infinity for f of x? As we move all the way to the right, the y value is getting closer and closer to 5. So this is going to match up with choice A. So question 8, there's a lot to read here, but anytime you hear the phrase directly proportional, a direct proportion is when you have something in the form of y equals k times x, where k is constant. So basically, as x increases, y increases. And if we have something that's an inverse variation, then in a situation like this, we would have x times y is equal to a constant. But notice in this question, we have the phrase directly proportional. So then what we have to do is just translate everything piece by piece. The rate of change of volume v is dv over dt. Is directly proportional means a constant times whatever the next phrase is, the cube root of the volume. The cube root of the volume would just be the cube root of v like this. Which of the following describes this relationship? So then we just have to go searching here. So if we just look a little bit carefully here, we can see choice B is going to match what we have written. So question 9, we have a slope field, and we're told that y equals f of x is the particular solution to the differential equation that passes through the point -1, 2. And then we have g of x is equal to this function. We want to find g prime of -1. Well, for this, what we could start off with, and then we could think about what we need, is we could just find what is g prime of x. And for this, we have to do the product rule. This is going to be 2 times x, and then we have f of x. And then we've got plus x squared times the derivative of f is f prime of x like this. So once again, we're just doing the power rule to take the derivative of the x squared, and the derivative of f is f prime, and ultimately we're using the product rule. So when we want to find what is g prime of -1, we need to know what is f of -1, and we also need to know what is f prime of -1. So for this part, if we look at the initial condition, the solution is passing through the point -1, 2. So that means f of -1 is equal to 2. And then if we want to find what is f prime of -1, we're going to go over to the slope field here at -1. And notice our y values here are going up. So we go up to the point -1, 2. And then we're just identifying this slope here. And the key here to finding what is this slope is you want to think of rise over run. And notice that we're aiming at this point here over at -2, 1. So to get from this point to this point, we're going to go up 1 over 1. So that tells us that the slope here of this tangent line is equal to 1. So that's our value for f prime of -1. So now we're just going to work this out. We're going to find g prime of -1. And this is going to be equal to, we have 2 times -1 is -2. And then we're multiplying by, we have f of -1. And then we have plus -1 squared is 1. And then we have f prime of -1 like this. So now we just plug in. This is going to be -2 times f of -1 is 2, plus f prime of -1 is 1. So this is going to give us -4 plus 1, which is -3, and that's going to match choice B. So question 10, we have another slope field and we want to match it to the differential equation here. So for this one, we're just playing a game of elimination here. Or what you could notice is that this is making a bunch of circles. So let's say you were to take something like this, like the equation x squared plus y squared is equal to 1. If you were to take the derivative of this equation with respect to x, what you'd have is you'd have 2x plus 2y dy dx is equal to the derivative of 1 is 0. And then if you want to solve this one here for dy dx, what you could do is you could subtract 2x on both sides. So now it's just algebra. You're going to have 2y dy dx equals negative 2x, and then just divide both sides by 2y. So this would have worked if we set this to be any equation. I mean, technically, I could say x squared plus y squared equals 1. I could even say x squared plus y squared equals r squared, where r represents the radius. And this would still give us the equation that we have here in the second line. And after we simplify here, we divide both sides by 2y. We're going to have 2 over 2 canceling, and this is going to work out to negative x over y. So this is going to match choice C. So now we're on to the BC stuff here, and first up we have Euler's method. So here's our starting point, here's our differential equation, and we want an approximation for y of 1.8. We're using Euler's method with two steps of equal size, starting at x equals 1. So for these kind of questions, I highly recommend that you make a table here. So you have x, you have y, and then you have dy dx. So for this, what I like to do is I think about we're starting at x equals 1. And we're trying to approximate what's going on at 1.8. And if you go from 1 to 1.8, that's a distance of 0.8. So since we're taking two steps of equal size, that tells us our middle value would be 1.4. And you could just do a quick check here. If you do plus 0.4 and then plus 0.4, those are two equal steps that get us to 1.8. And now at x equals 1, our y value is equal to 3. And then what you do from here is you plug your x and y into dy dx here. So we're going to have x minus y, or 1 minus 3, is going to give us negative 2. And then once you complete a row, that's when you write the equation of a tangent line with this point and this slope. So we're going to have a slope of negative 2, that's from our derivative. And then we have x minus 1, our x coordinate here. And then we have y minus 3 equals. Now, when I'm doing this work on my actual paper, I go ahead and just add the 3 to the other side. I don't bother writing the step before it, but this is just to show all the steps here that we're writing the equation of a line. So now what you do is you use the tangent line to evaluate this second row here. So we're going to get an approximation for y at 1.4. So now when we plug in x equals 1.4, we're going to have, or I'll just draw an arrow here, we're going to have that y is equal to negative 2 times, if you do 1.4 minus 1, that's 0.4. And then you've got plus 3. And if we simplify this here, this is going to give us negative 0.8 plus 3, which is going to give us 2.2. So that's going to go in this y column here. But now what you do is you start the process all over again. For the AP test, they usually just make you do 2 steps. 3 steps would be a little bit mean because this is a very tedious process. So now what we do is we're going to take dy dx, we're going to plug in 1.4 for x minus 2.2 for y. And if you subtract those two, you'll notice that those two values are 0.8 away from each other. So but when we subtract, the y is a bigger value here. We're going to have negative 0.8 like this. So now we go to the next line. We're going to write the equation of a tangent line. We have a slope of negative 0.8. And then we have x minus 1.4 like this. And then we have y minus 2.2. But if I have y minus 2.2, I would add the 2.2 to the other side. So now I'm just going to the equation of a line step. And then the last thing we're going to do here is plug in 1.8 for x. So at x equals 1.8, we plug in, we're going to have y equals negative 0.8 times 1.8 minus 4 is 0.4. And then we have plus 2.2. So this without a calculator can be a little bit annoying, but if you're doing this in your head, what I think of is okay, 8 times 4. So 8 times 4 is 32. But obviously 32 wouldn't be the product of these two. So if we work this out here, multiplying 0.8 by 0.4 would make this original term smaller in absolute value. So this would be negative 0.32 like this. Okay, so that's how we would work this out. And then plus 2.2. So then from this step, I would just do the long subtraction off to the side. We have 2.20 minus 0.32 like this. And I'm just going to work this out. We're going to borrow here. 10 minus 2 is 8. Borrow here to make this a 1. 11 minus 3 is 8. and then 1 minus 0 is 1. So this is going to work out here. We have 1.88 is our approximation for y at 1.8. Choice B is our solution. So question 12, we have brown bears in a forest. B of t tells us the number of brown bears, and it satisfies the logistic differential equation given over here. So t is the time in years, and we are told here b of 0 equals 20. What is the limit as t goes to infinity of b of t? So we had questions like this earlier, but the logistic equations are unique to the BC section. So with these, what I highly recommend that you do is you look for when would db over dt be equal to 0. And if we work this out here, we would set each factor. We would have 0.3 b equals 0, and we would have 1 minus b over 100 is equal to 0. And if you solve both of these equations, b equals 0 is going to come from the first one. And then this one you could probably just do in your head. 1 minus 1 is 0, so b would have to be 100 in order for this to work. And then what we could do is we could just draw a little sketch here. A logistic differential equation kind of looks like it's in the shape of an S. So it goes up in an S shape, and then it switches concavity right at the halfway point. So looking at this here, b equals 100 represents our carrying capacity. So this is just throwing out some common vocab here. So we have the carrying capacity, which is essentially like the max value here of the whole system, that the population of brown bears is not going to go past 100. And then 0 here represents kind of like that lower horizontal asymptote. But we were told that b of 0 is equal to 20. And that's important because that tells us that we're in between the asymptotes. So at the mark here at 50 is when this curve would change concavity. So this S shape here is going to go up like this. And then right at 50 is where the graph is going to change from concave up to concave down. So that's a significant value here like this. At the 50 mark, this is a point of inflection. Just so that we review all stuff about logistic differential equations here, because any one of these topics could pop up in the multiple choice. So here, now let's think about it. This is a graph of b of t that we just sketched here. And we want to know what is the limit as t goes to infinity of b of t. That's just going to be 100 here. That's going to be the carrying capacity of the graph. Some other questions they could ask off this would be, what is the rate of change when the rate of change is at its maximum? Just know at the point of inflection, this is the maximum growth rate is at this exact location here where the graph changes from concave up, since the slopes are increasing, but then they immediately start to decrease when we switch to concave down. So now we're moving to the free response here. Calculator use is still not permitted, and here we have a differential equation, and y equals f of x is the particular solution with this initial condition, and we're just going to sketch the solution curve here. So we're going to use this initial condition here that f of 1 is equal to 4. So over here at x equals 1, we have y equals 4. So this is our first point on our solution curve. And then what we're going to do here is we're just going to follow this direction field here. Notice that something you don't want to do with these questions, you see how all the arrows are kind of pointing up like this. You don't want to go against the arrows like this. Like that would be bad. So you don't have to be an amazing artist here, but we're just going to go ahead and draw something going like this. And then notice that as we head in the other direction here, that we're heading towards a horizontal asymptote at y equals 3. So once again, this line here is very important. At y equals 3, we have a horizontal asymptote. So we just have to make sure that our curve approaches this line. So for the next part here, we want to write the equation of the line tangent to f of x at x equals 1, and then use that line to approximate f of 1.2. So for this, we need to know the equation of a line. We have y minus y1 equals m times x minus x1. And another detail here, you could just add the y1 to the other side and just jump right into it like this. So we have m times x minus x1, and then we have plus y1 on the outside. So here, what we need to know is we need to know the slope at x equals 1. And notice at x equals 1, we have y equals 4. So we're going to plug the point 1, 4 into our derivative dy dx. So this is what we're going to do here. So we have the point 1, 4, and this is going into our derivative, which is only in terms of y. So we're just going to have negative 3 times 4 plus 9. So the derivative is something that is only dependent on y. So here what we have is we have negative 12 plus 9 is negative 3. And now we could write the equation of our line. So our line is going to be, we have y equals, and our m value we just found is negative 3. And then we've got x minus, our x coordinate was 1. And then we have plus 4 on the outside. And just know for the AP test, you don't actually have to solve for the equation in mx plus b form. You could just leave it like this. Because what's helpful is for the next part here, we want to find what is f of 1.2. So for this stage of the question here, when we want f of 1.2, we're going to say this is approximately equal to, and we have negative 3 times, we've got 1.2 minus 1. So now we're just replacing the x with 1.2. And then we tack on our plus 4 like this. And when we simplify this here, 1.2 minus 1 is going to give us 0.2, and 0.2 times negative 3 is going to give us negative 0.6. So we have negative 0.6 like this, plus 4. And for the AP test, to be honest, we could just leave our answer like this. We don't actually have to simplify in the free response section when you don't have a calculator. But just to see what this works out to, this is going to work out to 3.4. So this is going to be our approximation for f of 1.2. So for part C, we just have to determine if this approximation is an over or under estimate. And if you just look at the picture here, our curve is looking concave up because it's kind of smiling at us here. So the tangent line is going to sit under the curve. So anytime I need to remember this idea of is my approximation an over or under estimate, I just imagine what it looks like. So if I have something concave down like this, I would have an over approximation because my tangent lines would sit over my curve like this. But if I have something concave up, the tangent lines are under. But remember, we have to explain our reasoning here, so we just need something more precise. So how do we know that we're always going to have, or in this situation, we're going to have an under approximation? We have to make the argument that our curve is concave up. And that's going to come from our second derivative. So we have to take the derivative of dy dx. So we could say d squared y over dx squared is equal to negative 3 dy dx. But now, if we just think about this carefully, if we make another substitution here for dy dx, this is going to be equal to negative 3 times, and we have negative 3y plus 9. But I'm going to factor this a little bit more. I'm going to take another negative 3 out, and then negative 3 is going to multiply by this negative 3 to make 9, and we'll be left with y minus 3 on the inside. So just a little bit of algebra here. And now just think about this. Remember what we said before. We have a horizontal asymptote at y equals 3. So that means our function y equals f of x. If we look here, y equals f of x is going to be greater than 3 for all x. So the way we have this drawn here, based on our derivative has a horizontal, is telling us we have a horizontal asymptote at 3. So our function y equals f of x is greater than 3 for all x. So if you think about that here, if y is always greater than 3, then we have a positive times a positive is positive. So this tells us our second derivative is greater than 0 for all x. And the reason being here, because our function y equals f of x is greater than 3. So now the conclusion we can draw here, since our second derivative is positive for all x, that means our function y equals f of x is concave up for all values x, which would then tell us that our approximation is an underestimate. So part D is the most involved, separation of variables to find the particular solution. So we're starting off here with dy dx equals, we have negative 3y plus 9. And you could just do the algebra very quickly and just get up to this step here. I know, fast, come on, hurry, like you gotta be at work. So for part D, this is the most involved here. We have dy dx equals negative 3y plus 9, and we want to solve for the particular solution y equals f of x with this initial condition here. So if your algebra is really strong, you can just jump to a step like this, just separate variables and get to this step. You want to get the y terms with the dy and the x terms with the dx terms, even though there is no other x term here. But if you don't see that algebra real quick, you could just always write this as over 1 and cross multiply, and then you'll have dy is equal to negative 3y plus 9 times dx. And then you could divide both sides by negative 3y plus 9. Okay, but this is, once again, just like the algebra steps. And then once you get to this part, this is where you're going to integrate both sides. But you could do a u substitution on the left side, but there's an easier way to do this. Just factor out the negative 3 on bottom. So you could rewrite this, and we'll do that over here, as negative 1/3 integral, and then you have dy over, and you're going to have y minus 3 on bottom like this. And you could just imagine here, when you send this back in, just imagine you multiply the bottom again by negative 3. It's going to bring you right back to the previous step. And this is equal to integral, and then we have dx. So now the next part here, we're going to write, we have negative 1/3 times the antiderivative of dy over y minus 3 is going to give us natural log absolute value y minus 3. And we don't have to worry about doing a u substitution here. So this part I'm doing in my head is because we know the derivative with respect to y of y minus 3 is equal to 1. So anytime you're thinking about u substitution and the derivative of your u term is 1, that means you don't have to do u substitution. So for the next part here, the antiderivative of 1 is x, and then we have to tack on our plus c. So this step here is our general solution, but then what I like to do is I plug in at this step. I don't solve for y yet, I solve for y at the end. So I'm going to plug in here the initial condition. We have x equals 1, y equals 4, and that's going to give us, we're going to have negative 1/3 natural log, absolute value of 4 minus 3 is 1. And then this is equal to, we have 1 plus c like this. So now we just have to know here the absolute value of 1 is positive 1. So we could just drop the absolute value like this. One thing I'm mindful of here, you don't actually have to write this at the AP test, you just have to think it, is that there is no sign change. So since there's no sign change later on when we do the algebra, we could just drop this absolute value here. And now natural log of 1 is 0, so this tells us 0 equals 1 plus c, which tells us that c is equal to negative 1 like this. So now we take our value of c and plug it back in. So we're going to have negative 1/3 natural log absolute. Now we could drop the absolute value because of the no sign change idea. So now we just have this is equal to x minus 1. So from this step here, now it's just algebra, but from here to the answer is just one more point on most of your AP test. So if you get this far, you got either 4 out of 5 points or 5 out of 6 points. So this is like pretty solid work so far. So I would just multiply, and I don't know why I wrote negative 1. I would multiply both sides by negative 3. The reason being is I want to get rid of this negative 1/3. So we're doing negative 3 times negative 1/3 is going to give us just 1, and then we have natural log of y minus 3 equals, we have negative 3 times x is negative 3x, and then we have plus 3 at the end. So now at this step is where we could exponentiate both sides. So we'll raise both sides as powers of e, and then e and natural log cancel out, so we have y minus 3 equals e to the negative 3x plus 3, and now to solve for y, we're just going to add 3 to both sides, and we're going to have y equals 3 plus e to the negative 3x plus 3, and here is our particular solution. So now we're moving on to the BC free response, and we can use a calculator for this part. So we have 300 students at Bear Trap High School, and one day, calculitis, a rare disease, begins to spread at a rate modeled by this logistic differential equation here with this initial condition. And what we know here is that no one recovers from this rare disease. And first up, what is the rate of growth when the disease is spreading at the fastest rate? So what you need to know about logistic curves is that they take this general shape here. They approach this horizontal asymptote, which we call the carrying capacity, and they're in the shape of the letter S, but it's kind of like a stretched out S like this. So the curve starts off here as concave up, and then at the point of inflection here, it switches to concave down. So that point here is when the rate of growth is going to be the fastest. And you could just visualize that here. If you look at the slopes, you see the slopes of the tangent lines are increasing, and then at the point of inflection, that's when the slope is the greatest, and then the slopes start to decrease here. They start to decrease towards 0 as t goes to infinity. So this would be t, and this would be p of t. So for this, I can't memorize formulas, but I do know the basic concept of a logistic curve. As t goes to infinity, so this is part of the thought process. As t goes to infinity, so this is a big idea, the slope, in this case dp over dt, is heading towards 0. So what that helps me with is I look at the part of the logistic differential equation. This part here, if I set equal to 0, would give us p equals 0, which tells us as we get close to p equals 0, you see how the slope is also approaching 0 over here. But the real useful part is the second factor, 1 minus p over 200. If we set that equal to 0, this tells us that p equals 200 is our carrying capacity. Okay, so that is essentially like the upper limit on our curve here. So that I'm just going to label up top. This is going to be at 200, but the growth rate is fastest at the halfway point. So half of 200 would be 100. So now to answer this question here, what is the rate of growth when it's spreading the fastest? Well, we would just take dp over dt, and we're going to plug in p equals 100. So we're plugging in p equals 100. And now we just substitute. We have 0.1 times 100 times we have 1 minus 100 over 200 is a half. And then we just have to multiply this out. So this would be half times 100 is 50, and then 50 times 0.1 is going to give us 5. But now the units here, notice that the P represents students and T is measured in minutes. So this would be students per minute. So what this tells us, at the fastest rate here, that 5 students per minute are going to get calculitis, this rare disease. So this is our solution to part A. So now for part B, we could use the sketch that we made up top to find what is the limit as t goes to infinity of P of t. And you could see here, as t goes to infinity, our function is approaching the line y equals 200. So that's our limit here, but we have to explain what this means in the context of the problem. This tells us that no more than 200 students are going to contract calculitis. Now, if this is a type of question that you struggle with, just go back and think about what is the meaning of P of t. P tells us the number of students infected with calculitis. So that helps me construct my sentence here, that the limit approaching 200 tells us that no more than 200 students will be infected. So part C, we're using Euler's method. We're starting here, taking 2 steps of equal size, and we're going to approximate the number of students infected at t equals 4 minutes. We're rounding to the nearest integer, which makes sense because we're talking about students here, so we're just going to have whole numbers. So what we have here is, I like to make a table. We have t, we have P of t, and then I'm going to write the derivative dp over dt. So we're starting at t equals 0 and p equals 20. So what I'm going to do here is use the calculator to find dp over dt at p equals 20. So we could just plug in. We have 0.1, and we're going to multiply by 20 because we're plugging in p equals 20 first. And then we're going to have, in parentheses, 1 minus. And if we struggle to type this in, just press alpha y equals enter to pull up a blank fraction. And p is still equal to 20. We're dividing by 200. And now we just go to the right here, close this, and this is going to be our rate of change to start. So now let's just record that slope. We have 1.8 here, and from this step, we're just going to write the equation of a tangent line with this point and this slope. And one thing you might be mindful of here is that this is actually going to be the y-intercept because we're starting at the point 0, 20. So for this one, we could use the formula y minus y1 equals m times x minus x1, so this formula here. But in this situation, this is one of those unique situations where I would rather use this formula because, once again, we're starting with the y-intercept. So our first tangent line, we're going to have y equals, and we're going to have m, our slope is 1.8. And now instead of x, I'm going to put t here because we're talking about time, plus our y-intercept here is 20. And then notice we are going to approximate what's going on at t equals 4 minutes. So if we're taking 2 steps of equal size, the halfway point is going to be at t equals 2. So that's the first value of t that we're plugging in. We're going to have y of 2 is equal to, we have 1.8 times 2 plus 20. And now this is something we could use a calculator for, or this is just going to be 3.6 plus 20, and 3.6 plus 20 is going to give us 23.6. So this is going to be our midway y value. And then what we need to do from this step is we need to find what is the derivative dp over dt at p equals 23.6. So now we're plugging in 23.6 into our derivative. So we have 0.1, and then in place of p, we're writing 23.6. And we're going to close the parentheses here, open a new one. We're essentially writing what we have above, but instead of 20, we have 23.6. So we're just going to put in another fraction here. And now at 23.6, we're dividing by 200. And we get out of this, close the parenthesis, and here is our new slope. So we had 2.08152. And now with these combinations of points and slopes, we're going to write the equation of one more tangent line. So this time what we have is we have y minus the y value is 23.6 equals the slope is 2.08152 times t minus 2 like this. And now for this, I would just add the 23.6 to the other side. So that's something that we could just do all in one step here. I'm just going to add that to the other side like this. So plus 23.6. And might as well move that y over so it looks a little bit neater. So this is our new tangent line, and this is going to get us our approximation here. If we want to find an approximation here for p of 4 is going to be roughly equal to, now we're just plugging 4 into this equation. So we're going to have 2.08152, 4 minus 2 is 2, plus 23.6, and the rest is calculator work. So let's just type this in. We have the slope already here. We're just going to multiply it by 2, and then we're going to add 23.6. And we're going to round to the nearest whole number when we write out our final solution, but we have 27.763. So we have 27.763, but now let's just make sure that we round to the nearest integer here. We're going to say that 28 students are infected with calculitis at t equals 4 minutes. This is our approximation. So for the last part here, this is the most involved. We're going to solve for the particular solution y equals p of t with the initial condition p of 0 equals 20. So for this, I would start by multiplying both sides by dt. And that's going to give us dp equals 0.1 times p. And we have 1 minus p over 200. And we're just going to tack on the dt here. And then what we could do is divide both sides by the factors p and 1 minus p over 200. So that's what we're going to divide both sides by. We have this times this going on both sides. So from here, what we have to do is we have to do partial fraction decomposition. And this is a very lengthy process. But before we actually do that, I want to look at the step we're at now. We're at dp over p, and we have 1 minus p over 200. At this step, what I don't like is what's going on the inside here, this 1 minus p over 200. And what we have on the right side is just 0.1 times dt. So what I would actually want to do on this side over here is I would multiply the top and bottom by 200. And the reason I want to do this is when we distribute the 200, it's going to wipe out that fraction inside here. So now I'm going to write that result over here. We're going to say we're carrying on over here. And we're going to have 200 dp like this over, and we're going to have p on bottom. But when we distribute the 200, we're going to have 200 minus, and when we do 200 times p over 200, we're going to be left with just p like this. So this is a way, way, way better looking setup here, so that when we start to integrate now, this is going to be way easier to deal with. So now we could go ahead and integrate both sides. However, what we have to do for this is we're going to actually have to do some algebra. We're going to do a partial fraction decomposition. So this I like to think of as kind of like a side quest here. So this is just algebra that we're doing in this section here, that I'm going to take 200 over p times 200 minus p, and I'm going to set this equal to, we have a over p plus we have b over 200 minus p. And now for something like this, what you want to do is you want to make common denominators between these two terms. So for this, I'm actually going to just move this over a little bit just to make space. And what we need to multiply by here, we have to multiply this term by the denominator of this term on top and bottom. So we're going to be multiplying by 200 minus p over 200 minus p. Okay, so this is just, once again, all algebra, but it's like particularly painful algebra. So what we're going to have in this, once all the denominators match, we could essentially cancel everything out. And this is going to give us the equation 200 equals a times 200 minus p plus b times p like this. Okay, so that allows us to get to this step. And then from here, if we want, we could just erase what we included. So this is algebra, to be honest, that I just do in my head. And it allows me to go from this line to this line. And then what I recommend that you do is you plug in test values. So if you plug in p equals 200, that's going to wipe out this factor. And you're going to have 200 equals a times 0 plus p is equal to 200. You have 200 times b. And now this is going to be gone, and 200 equals 200b tells us b is equal to 1. And then I would substitute in next p equals 0, and that's going to give us 200 equals 200 minus 0 is 200, so we have 200a plus b times 0. Now b times 0 cancels, telling us that a is equal to 1. So what this allows us to do is it allows us to complete the partial fraction decomposition for this fraction here. So we can now claim that 200 over p times 200 minus p is equal to 1 over p plus b is also equal to 1. We have 1 over 200 minus p like this. So let's break this thing up here. The left side is the complicated piece. We're going to break this up now. The integrand on the inside, we said this integrand can break up to 1 over p plus 1 over 200 minus p like this. And then we'll just tack on the dp on the outside like this. So from here, this is equal to the integral of 0.1 times dt. And now we could just anti-derive. So one little shortcut here, when you're integrating any sort of fraction where you have a linear factor on bottom, something in the form of mx plus b, I know right away that this is going to be natural log absolute value mx plus b, and I tack on my plus c. However, a sneaky step here is you have to take the derivative of the bottom, and the derivative of the bottom in this case is m, and we just write 1 over m in front. So that's how I'm going to handle this piece over here, because this piece is not a problem. It's just this one we have to be a little extra careful. So this is going to work out to natural log absolute value p, and then I'm going to leave a space. We have natural log absolute value 200 minus p, However, we have to be mindful here, the derivative of 200 minus p is negative 1. So I'm just going to tack on a minus like this. And this is equal to 0.1t. And then we tack on our constant here, plus c. But remember, p of 0 was equal to 20. So what this tells us, if we plug in, we're going to have natural log of 20, because the absolute value of 20 is just 20, minus natural log, and we have 20 subtracted from 200 is going to give us 180, and the absolute value could drop for this as well, is equal to 0 plus c, because t is equal to 0 here. So that gives us this. And now what I would do is just combine this into a single log. This I would just say is c equals natural log of 20 over 180, and this simplifies here. The common zeros chop, this is just natural log of 1/9. And now once we have our constant of integration, we could plug it back into this general solution here. And what we're going to have is we're going to have natural log of, and remember the absolute value just drops, so we could just say ln p minus ln 200 minus p on the inside. And this is going to be equal to 0.1t, and then plus we have natural log of 1/9 like this. And now the rest is algebra. So from here I would group these into a single log term. We have natural log of p over 200 minus p like this. And now this we could just set equal to, we have 0.1t plus natural log of 1/9. And then from this step, I would exponentiate both sides, make both sides powers of e. And then this term is going to cancel here. We'll start writing the results over here in this little space. And what we're going to have is we're going to have p over 200 minus p is equal to e to this power here. And if we want to clean this up a bit, this is just a side note. Notice that this could be rewritten as e to the 0.1t times e to the natural log of 1/9, and this would just cancel out like this. So e and ln would cancel out if we break this apart, and this would just be equal to 1/9 e to the 0.1t. So this will just clean it up a little bit and make it look nicer on the right side. So this we could say once again is 1/9 e to the 0.1t like this. And now the rest, we're just solving for the variable p. So we're going to multiply both sides here by 200 minus p, or you can just think of it as we're cross multiplying. And we're going to have p equals, we're going to have 200 times 1 over 9, so 200 over 9 e to the 0.1t. And then we're going to multiply this expression here by minus p, so we have minus p times 1/9 e to the 0.1t like this. And once again, that's just equal to p, but we need to get these terms here on the same side. So I'm going to add p times 1/9 e to both sides. And that I'll just show in the next step here like this. We have p plus, and then we have p times 1/9 e to the 0.1t like this is equal to, we're left with this piece on the right side, 200 over 9 e to the 0.1t like this. And now the rest, we're just going to factor out a term p here. So this, I'll just show this step on the side. This is p times 1 plus 1/9, and we have e to the 0.1t. Okay, just because I want to do this in less steps here. So if we factor out a p, we're going to be left with this factor here on the left side. So then we could just say here that p is equal to, we have 200 over 9 e to the 0.1t like this, and we're going to divide by that leftover factor is 1 plus 1/9 e to the 0.1t. And now at the AP test, we don't actually have to simplify this. But if you want to make this look real nice here, you could multiply the top and bottom by 9, and that's going to tell us that p equals, we would have 200e to the 0.1t over, and then if we multiply the bottom by 9 as well, we're going to have 9 plus e to the 0.1t. And here is our solution to the logistic differential equation.